In this video, we're going to discuss multi-component gas and liquid systems. And by multi-component, I mean that not only are we going to deal with systems that have multiple phases, but we're also going to deal with systems that have multiple chemical species at the same time. Now, whenever we're dealing with chemical reaction and separation processes, many times they involve multiple chemical species that are transferring between different phases. And many times those phases are between the gas and liquid phases. Right? And so many chemical reaction and separation processes involve the transfer of multiple species between gas and liquid phases. And so in this section, I want to discuss the thermodynamic tools we could use in order to understand these systems. But before I dig into the math, I first want to discuss the physical picture that these thermodynamic tools are trying to describe and model. Okay? So let's discuss the physical picture. And so I want you to consider the following system. All right? And so let's start out with just a rectangle, or square, I guess. All right? And in this square is going to represent the boundaries of our system. Okay? And let's consider a system in which we have two phases, where we have a vapor phase on top and a liquid phase on bottom. And the system is at some temperature T1. Now, in the liquid phase, let's say we have an equal molar amount of A molecules and B molecules. Okay, so we have 4 A molecules here and 4 B molecules as well. 3, 4. In the vapor phase, let's also say we have an equal molar amount of A and B. But let's say that there's fewer molecules in the vapor phase than the liquid phase, right? Let's say that T1 is a fairly low temperature, right? And so this is the picture of the system in the initial conditions. Let's then say we heat the system. We add heat to it so that we can change the temperature, right? But before I draw the picture of the system at the second temperature, I first want to say that let's consider the case where the B molecule is more volatile than the A molecule. And when I say that, what I mean is that let's pretend that the B molecule is much more easily vaporized than the A molecule. Right? It's easier to get B into the vapor phase than it is A. One way you could characterize that is you could also say that the boiling point temperature for B is less than the boiling point temperature for A. All right? And so we're considering the case where B is more volatile than A. So then, let's say we heat our system so that it goes to a new temperature where T2 is greater than T1. All right? At the temperature T2, we're still going to have a vapor and a liquid phase. But because we added heat to the system, that allows some of the molecules from the liquid phase to go into the vapor phase. All right? And so we still have some A and B molecules in the liquid phase, but a lot of them are now going to the vapor phase. But we have to remember that I said the B molecule is more volatile than the A molecule. And so when we add heat to the system, it's much more likely that the B molecules are going to go into the vapor phase than the A molecules. All right? And so down here, we have more A molecules, okay? And so because the B molecule is more volatile than A, what ends up happening is that even though at the beginning we started with equal molar compositions of A and B in both the liquid and vapor phases, now when we add heat to the system, what ends up happening is that our vapor phase has more B molecules in it. So the vapor phase becomes enriched in B, while the liquid phase is left over with more A molecules, right? And so the liquid phase becomes enriched in A, okay? And so with these thermodynamic models, what they're trying to do is they're trying to describe the sort of physics that we're seeing here. The case where if we add heat to the system with molecules that have different volatilities, how can we describe the fact that one of the phases ends up enriched in one molecule and the other phase is enriched in the other molecule? That's what these models are trying to describe.